Hi there, I'm Nick Karpowitz from the Max Planck Institute of Quantum Optics, and I made an open source nonlinear optics simulation called Lightwave Explorer, so link is in the description. In the new update, I made it easier to work with one of the more complex details of one of the propagation modes, FDTD, which stands for finite-difference time domain. And I want to show in this video how it works. So just as a bit of background, FDTD is one of the approaches to simulating electrodynamics, and it's one of two in Lightwave Explorer. The other one is called the unidirectional pulse propagation equation, or UPPE. So FDTD is based on having a finite-sized volume of space where the simulation is carried out, and then stepping forward in time, watching how the electromagnetic wave propagates through this medium. So for example, if we have a nonlinear crystal, which we can simulate in Lightwave Explorer sort of as the default when we're using FDTD mode. So here I have a thin fused silica. The light can propagate through this crystal, and we'll see the primary light which passes through the crystal and also a reflection taking place inside of this crystal. And this happens because we're looking at the full electric field, simulating it everywhere in space. If we're doing the unidirectional pulse propagation mode, these reflections won't appear. So we can go here, and you'll see you get a similar electric field coming out, but we don't have this trailing reflection. And this is because the UPPE is unidirectional, so this isn't compatible with having reflections inside of the crystal. So sometimes this difference doesn't really matter. If you have a thick crystal with a low refractive index, the reflections barely change the output. But in thinner crystals, the reflections can matter a lot. And that's where you would want to use FDTD. And this is also compounded by the time it takes to run the simulation. So in UPPE, the simulation time scales linearly with the length of the crystal. You make the crystal twice as long, the simulation takes twice as long. In FDTD, the crystal, if you make it twice as long, then your grid has to be twice as big. So there's twice as much volume of space that has to be simulated, so each time step takes longer, twice as long, and it also takes the pulse longer to propagate through the medium, twice as long, so you get a factor of 4. So in general, it's going to scale with the square of the length of the crystal, whereas UPPE is going to scale linearly with the length of the crystal. So those can matter a lot once you get into thick crystals. So FDTD is kind of better for smaller grids. In the end, it's going to be limited by how much memory, especially GPU memory, you have. Another advantage of FDTD is sometimes we don't want to just simulate a crystal with two flat surfaces. We want to simulate the transmission through a more complex grid where we have different materials in different positions in space. And so next we have to be able to tell the simulation what materials are where. In Lightwave Explorer, you can do this by importing a file containing a map of materials. And in the latest version, I made it easier to access this. And I think the easiest way to see how it works is with an example. So first we have to make the file that we put into the simulation. And in order to make this easy, I made a Jupyter notebook, which you can find in the documentation folder on the GitHub repo. This notebook is going to construct a grid for us. I'm going to make a simple simulation as an example. So just two-dimensional, 256 points in the X and Z directions and just 1 point in the Y direction, and with a grid resolution of 25 nanometers. So we'll set up this grid, and I'll just put a 1 micron radius rod in the center. And so once we make that, you can see, so where it's yellow, that's where there's material, and everywhere else there's vacuum. And then this will write the file in the format that we need. It looks like this. There are just two parts of it. On the top is a header, which describes all of the materials that are on the grid. So it gives the index of its position in the crystal database. So this is fused silica in this case. And then different properties that we want to apply to this material, mostly talking about any plasma that might be present inside of the material, or if it's a birefringent crystal, maybe the theta and phi. We tell it the dimensions of our grid, and then beneath that we have the grid, which you can see here. There's just a bunch of zeros. Where it's 0, there's vacuum. If we look more towards the center of the grid, we can find the crystal, or not the crystal in this case, it's just a few silica rod. But wherever there's a 1, there's material. Wherever there's a 0, there's vacuum. So we're just giving the simulation a map where the material is. So the distribution of objects inside of this plane. So we can load this into Lightwave Explorer here. And so first I will empty our optics database, and you can load a file into the optics database just by clicking this button here. And now we will go load our grid. It tells you the index in the optics database that it loaded your file into. And now we can run the simulation on this grid using the FDTD sequence function. And this is one of the things that I changed in the new version to make it easier to work with this. You can see there's a few input parameters. I'll just tell you kind of one by one what they do. Yeah, so this is the FDTD function. If you look in the tooltip of the button, which will sort of put a default version of this, it will also tell you what each one is, so you don't have to memorize them. Just look at the tooltip and it will show you everything. So you can see here that the first argument is a time divider. The time steps that you need in an FDTD simulation tend to be quite small. I mean, it's good if it's about 1/8 of the period of the light that you want to simulate, or smaller. And, well, you don't really need all of that detail in the file that you save. So just to make the file sizes smaller, we can put a divider in there so we don't have to keep all of the points that are in the simulation. So if we put 5 here, it's going to divide our sort of main interface time step by 5 when it runs the simulation. So we have 125 attoseconds as a time step, so we're going to end up with a 25 attosecond time step in this simulation. The next parameter is the DZ, the Z step of the simulation, which we also set here. If this is set to D, it will just default to whatever value we set on the interface. And it's basically if you're mixing different simulations and running sort of a sequence where the output of one is going into the other, maybe you need a different Z step for different cases, and that's why I put it in here to make it controllable. And then the next two are buffers. So if you imagine we have a crystal, we can put some vacuum before and after in order to have a little bit of room before the electric field sort of hits the edges of the grid. They're set to 0 in this case because I just wanted to use the input grid with its real dimensions without expanding it at all. Next, we have our observation point, which tells us within the grid, where do we want to record the field as a function of time and space. So 3.2 here, since it's a 6.4 micron grid, 3.2 microns is going to be right in the center. So the first thing that we'll see is the field in the center of this fused silica rod. And then following that, we have a wait time. So this tells the simulation how long to wait before it starts recording the electric field, because it takes some time for the field to reach our plane of interest. So it doesn't make sense to record the field that we know is going to be 0. We can wait a little while and record the interesting part of the dynamics. And following that, we have a switch that lets us either save or not save the near field. So if this is set to 0, it's going to filter out spatial frequencies that won't make it into the far field. If we set it to 1, it'll preserve all of the near electric field components as well. So it just matters, it only matters if you're doing simulations afterwards. And finally, this 0 here is our index into our database. So when we loaded this file, it tells us index 0. We put 0 here to use the right grid. And if we put D here, it will just make a crystal in the center of the grid with a thickness set by the thickness parameter on the interface. But I will do 0 here, and we can look at propagation of light through the rod. So again, this is the field in the center. The first thing you see is that you can pretty clearly see where there is glass and where there is vacuum, right? And wherever there is glass, we've bent the wavefronts. So it's focusing, like you would expect, this round, higher refractive index object to do. So it's focusing inside of the rod. And actually we also see the reflection coming from the other side of the rod going back towards the center. This is electric field versus space in the vertical axis and time on the horizontal axis. So later in time, we see the reflection coming back. And this is because we have our observation plane in the middle of this rod. So now we can put our observation plane after the rod and look at how the electric field has changed. Now you can see now it's focused a bit more. The edges of the rod are a little bit blurry because the field has now exited this interface. There's a bit of diffraction going on. There's no reflection anymore because we are outside of the material. We would have to wait a little bit longer for the reflection to come all the way back from the other surface of the rod. And of course we can turn up the intensity of our light to look at the effects of Kerr effect and third harmonic generation inside of this little rod as well. So that's pretty cool. That's a quick intro to FDTD mode in Lightwave Explorer. I hope you have fun playing around with it. The GitHub repo is linked in the description. You can find downloads for Windows and Mac, and on Linux it's on FlatHub, so it's easy to get there. Let me know if you find any bugs. Subscribe if you'd like to keep up to date with this stuff, and take care.